I'm beginning to record the lecture now. I should mention, you should always keep in mind that Mr. Carnot and company that introduced thermodynamics, they were not scientists. They were engineers. Their goal was understand how the steam machine was working. That was the perspective, how machines burning energy and converting them into work were working. So they had a completely top to bottom approach. They introduced these macroscopic concepts such as heat, entropy, and these were profoundly useful concepts because using these concepts, you can introduce uh, the notion of the efficiency of a machine, right? You can understand what is the upper limit of the work a machine can produce, how much work you're obliged to pull in if you want to extract heat from the system, and so on and so forth. So this was really an engineer's perspective. So now, really, since we believe that, you know, at least from some, say, nanometers up, nature is very well described by classical mechanics, we should be able to recover all these concepts starting from a bottom-up approach. And in the bottom-up approach, we can think about the Hamiltonian dynamics being at the lowest ground state. And then, you have the stochastic dynamics, which is the result of integrating out the Beth from the Hamiltonian dynamics. And from here, we want to um, recover thermodynamics. And the idea is that we want to, you know, to give really a meaning to the word dynamics that enters in the word thermodynamics. Because, like I said the other time, dynamics means something that changes in time. But when you do theories of ensembles, give theories of ensembles, you never have anything changing. You always talk about averages at fixed conditions. And in in thermodynamics, on the other hand, you talk about reversible or irreversible processes in which, although adiabatically or non-adiabatically, you're changing the system. So you see, in thermodynamics, you are introducing this concept of transformation of your system. And you also, you know, allow yourself to consider non-infinitely slow adiabatic transformations, but arbitrary transformation, which you have a symbol for, right? You have your state function, and then you maybe draw things like this. Remember, to distinguish a reversible from an irreversible. And the way you distinguish within them is through the concept of entropy. You define an adiabatically slow system transformation, which is one in which the system goes through infinitely many equilibrium configuration. You call it reversible. And then you know that entropy along any reversible transformation should never change. The total system's entropy, total universe entropy. So if you want, you can use the absence of change of the universe entropy as a signature of a reversible transformation. And in fact, the two things come together. And the problem is typical questions where demonstrate that this process is reversible, and the way you would do it is by computing entropy variations. Or, likewise, you would consider an irreversible process, and you would go along a reversible process for which you were able to calculate the entropy variation of the system according to the famous law S is the change in the work along a reversible. transformation, and this was the change of entropy of your system, and of course the universe must have zero along it. The reversible transformation must be unchanged in terms of entropy balance, and so some equivalent reverse change of entropy must have occurred in the universe, in the bath, and so on. So now we really want to build this contact, and in order to do that, we need something to change sometime. So the theory of ensembles, equilibrium ensembles, may not be well equipped. However, the Langevin dynamics provides a generalization and extension that contains equilibrium as a specific case for the infinite time limit. But it's valid at any time between, say, delta t, my infinitesimal cutoff, and infinity. So this should be the right theoretical framework to tackle these issues.